G'day YouTube, Warbles on a lot here. I want to talk about counterintuitive evidence. To wit, I want to talk about the blizzard in North America and how it proves that global warming is getting worse. I know that's difficult for some people to stumble, particularly the people who don't want to believe that global warming is real, and also for the people who say that global warming might be happening but it's got nothing to do with human activity. Every time they see a snowflake, that mob likes to say, oh look, see, it's snowing over there, somewhere's got a cold day, therefore global warming can't be happening. And any time you say to them, oh well, you know, like last year Australia had the hottest day, the hottest week, the hottest month, and it was the 4th hottest year consecutively. And when you say to them that the world, you know, like every year for the last 13 years has been part of the 14 hottest years that the planet's ever had, they say, oh yeah, but that's all part of a natural cycle and it'll come back the other way sometime. So yeah, now they're trying to suggest that because there's been a blizzard in North America and a lot of people have been surprised by having to live at, 40 degrees below zero, which is where the Celsius and the Fahrenheit scale coincide, therefore global warming cannot be happening. And I posted a quick little movie grabbed from the ABC radio where a Canadian conservation biologist tried to explain how he'd put thermoprobes on narwhals under the Arctic Ocean, and he'd got definite proof that the Arctic Ocean's warming. It's warming faster than anywhere else on the Earth is warming, and he glossed over the physics of how come warming the Arctic Ocean causes blizzards in North America. Some of my subs didn't get the point. Some of them said that it was laughable. So I faved a movie that's been posted by Uptake Video, which features the scientific advisor to President Obama using a 2-minute animation to explain it. But in 2 minutes you don't give much depth or detail, so I thought I'd have a look through my old pile of New Scientist magazines. Hit a bit of pay dirt on the 26 October 2013 edition. Jetstream. The jet streams that dictate our weather seem to be changing, but how and what's to blame? Which then gives us a very nice photograph of the deadly dihydrogen monoxide condensing in the hot exhaust plumes from the 4 jet engines as the exhaust plumes cool, because there was almost enough water vapour in the inlet air to become a cloud, and once you burn hydrocarbon in the air, the hydrogen attaches to the oxygen in the air and that kicks it above dew point, so once the hot air cools down behind the engine, the dihydrogen monoxide becomes visible in the form of droplets. But, as I'm famous for, that was a sidetrack. So, let's get on to reading. As Deputy Director of the Japan Esperanto Society, it was clear what language Wasaburo Uushi would choose to publish his discovery in. Unfortunately, it meant that hardly anybody noticed. In the mid-1920s, Uushi, a meteorologist in his day job, was releasing research balloons near Mount Fuji when he saw something odd. Once the balloons had climbed high into the atmosphere above the clouds, they suddenly hurtled out eastwards over the Pacific. Persistent high-level winds, often stronger than a hurricane, were blowing from west to east over Japan. Other people had observed something similar in Europe, but Uushi was the first to put 2 and 2 together and pinpoint the existence of a permanent narrow tunnel of wind circling Earth at mid-latitudes, travelling at 100 to 400 kilometres per hour. Gradually, knowledge of the jet stream circulated around the globe too, albeit by unconventional means. See Fugo No-Go, page 40. So we jump ahead and we'll do that. Fugo No-Go. Wasaburo Uushi's pioneering research into the jet stream in the 1920s was essentially ignored in the West because he published his research in Esperanto. So says John Lewis of the US government's National Severe Storms Laboratory in Reno, Nevada, who's researched the affair. The turnaround came during the Second World War when, now in conflict with the US, Japan hatched a plan to surprise Uncle Sam by using the wind to express deliver bombs. Hydrogen balloons rode the jet stream from Japan, carrying incendiary devices that were timed to drop on arrival over land. There was also anti-personnel bombs and a small high explosive bomb on each gondola. Incendiary devices that were timed to drop on arrival over land. Guided by Uushi's wind charts, 9,000 bombs called Fugo were unleashed from Japan between November 44 and April 45. Luckily for the US, Japan's meteorologists got the timing wrong. The Jetstream was a little weaker than Uushi had calculated, and the balloons took 96 hours to cross on average, rather than the estimated 65 hours to cross the Pacific. All but 300 of them dropped their bombs harmlessly into the Pacific Ocean. One that did make it hit a power line, blacking out the Hanford nuclear weapons plant in Washington, which was then preparing the atomic bombs destined for Hiroshima and Nagasaki. Another Fugo bomb landed on a Sunday school picnic in Oregon, killing 6 people. The only combat casualties on the US mainland during the entire war. That made the West finally wake up to the Jetstream's power. Balloon bombs spoke louder than Esperanto. Well, that's an interesting perspective. What spoke even louder was the fact that the B-29s, which were trying to bomb Japan from high altitudes using daylight precision bombing like that worked against the Germans with the B-17s during the war on Europe, they couldn't hit the side of a barn over Japan because they were getting bucked around and blown sideways by the Jetstreams. They wound up destroying Tokyo in night incendiary raids at low level, and they burnt 10 square miles in one night. That's what made the West pay attention to the Jetstreams. Not the bloody balloons, the fact that the Jetstreams beat the B-29s. I trust you enjoyed that warble sidetrack. Today, surfing the Jetstream is commonplace. Slipstreaming on it eastbound can slice up to an hour off a flight across the Atlantic, and as we have learned more about the Jetstream, it has become clear that it is no rarefied curiosity. Its speed and path is the invisible hand guiding most weather systems on the continents below. When it falters, extremes of all sorts can result, from freeze-ups to droughts, heat waves and catastrophic floods. That makes it all the more worrying that, just lately, the Jetstream has seemed to be changing. But is it really? And if it is, how and why? Earth's atmosphere actually has several jet streams at different latitudes. The strongest are the polar jet streams, one in each of the northern and southern hemispheres. A few hundred kilometres across, these polar jet streams carve a sinuous path at the top of the troposphere, the lowest layer of the Earth's atmosphere. They lie anywhere between 7 and 12 kilometres up at latitudes generally between 50 and 70 degrees, although with periodic excursions beyond. Their origin is simple enough. Where cold, dense polar air meets warmer, lighter air from near the equator, winds rush in to equalise the pressure difference. Earth's west to east rotation diverts these winds from what would otherwise be a north-south trajectory to one travelling east. In the southern hemisphere, the polar jet encircles the Antarctic, mostly over the Southern Ocean. In the northern hemisphere, it passes over North America, Europe and Japan, some of the most densely populated places on Earth. And we feel its drag on the ground. The fronts and low pressure systems familiar in our weather forecasts are the jet stream's earthbound manifestations, as its high winds pull the air below around the planet. See diagram right. Polar air brings cold conditions to areas north of the jet stream. Underneath the jet stream, rapidly moving rising air produces changeable weather and plentiful rain. Areas south of the polar jet are influenced by warmer air from the equator. This is not to scale, and you've got a subtropical jet which is warm and a polar jet which is cold. And when they talk about the amplitude of the sine curve, that's what they're talking about here. And the troughs and the peaks move around the planet. When they talk about the polar jet getting stalled, they mean that the whole snake ceases to move and that low point hovers there. Let's move on with the story. That photo says, the jet stream conspired with Tropical Storm Sandy to bring devastation to the eastern US. That was last year, right? Most of Europe's weather rides in under the jet stream from the Atlantic, and most of the US's weather comes from the Pacific in a similar manner. If you are north of the jet stream, and so beneath air from the poles, it will be cold. If you are to the south, it will be warm. If you are under the jet stream's path as it sucks moist air upwards, water will condense and fronts will bring changeable rainy weather. But the jet stream does not follow a straight line. It meanders like a river on a flat floodplain, sometimes moving north and sometimes south. Most often such meanders are triggered by the stretching and squashing of the air as the jet stream passes over mountains. Known as Rossby waves, they travel slowly east, typically taking a week to cross North America, for instance. Occasionally they get stuck, generally when the jet stream slows, as a result of random fluctuations in the temperature difference between polar and non-polar air. That brings blocking highs within the loops of the malingering meanders. Bits of the globe get stuck under a vast tongue, either of hot, dry air stretching north from the tropics in summer, or of ice-cold air reaching south from the Arctic in winter. A couple of days of hot or cold, wet or dry doesn't matter much to most people, but a couple of weeks can matter a great deal. The long heat wave in Europe in 2003, a classic piece of sticky weather in all senses, killed an estimated 70,000 people. Meteorologists now blame the Dust Bowl in the US Midwest in the 1930s on a faltering jet stream that tracked south, diverting the usual rains and triggering drought in the blocking zone. Arctic heat wave. The jet stream has been particularly weak during several recent northern winters, meandering erratically and bringing polar air plunging as far south as Florida, where chilled iguanas fell out of the trees, and delivering long cold winters in Western Europe that, for some, made a mockery of the idea of global warming. The massive summer heat wave of 2010 that sparked forest fires across Russia also arose because an exceptionally long-lasting blocking high brought hot dry air up from Africa for weeks on end. At the same time, further east, another long loop in the jet stream pushed wet air down from the north towards the Himalayas, where it interacted with the Asian monsoon and delivered huge floods down the Indus River. At one stage, a fifth of Pakistan was underwater. A changeable jet stream and intermittent blocking highs have always been part of weather in the middle latitudes, but some researchers now see a worrying trend. In 2008, Christina Archer, now at the University of Delaware in Newark, and Ken Caldera of Stanford University in California analysed jet stream data from 1979 to 2001 and found a small but significant slowing of the northern polar jet stream during that period. In late 2012, James Overland of the US National Oceanic and Atmospheric Administration reported that the jet stream had been meandering more in the past 5 years than in the previous 30 years. Also, last year, Jennifer Francis at Rutgers University in New Brunswick, New Jersey, found that since the 1990s its average speed in autumn has fallen by 14% over North America and the North Atlantic, with its path growing more idiosyncratic. At a US Senate hearing in July this year, that's 2013, Francis went so far as to suggest that a weakened jet stream had caused Tropical Storm Sandy to take the unusual path that devastated parts of Manhattan last year. She was speaking days after Anchorage, Alaska, and Norilsk, Siberia, reported temperatures more akin to the Mediterranean, all blamed on blocking highs funneling heat north. Meanwhile, the southern hemisphere's polar jet has also gone walkabout, drifting poleward but strengthening in recent decades. There is strong evidence that both are due to the ozone hole in the stratosphere above. This southern drift may be reducing rainfall in the south of Australia because this area is now less often under the southern polar jet stream. In the northern hemisphere, however, Francis thinks something odd is afoot that has nothing to do with ozone holes. In March last year, together with Stephen Vivaris of the University of Wisconsin-Madison, she published her idea that the culprit is the rapidly warming Arctic. The Arctic is heating up 2 or 3 times faster than most of the rest of the planet, as white snow and ice that reflect solar energy back into space are disappearing to be replaced by dark, energy-absorbing ocean and land. This Arctic amplification means that the temperature difference between the Arctic and lower latitudes is diminishing. Since this difference creates the jet stream, it will weaken too. The dynamics are complicated, of course, but what we are seeing is the effect of Arctic amplification on the jet stream. I am convinced of it, she says. By no means everyone is persuaded by Francis's argument, however. Michael Lockwood at the University of Reading, UK, for example, doesn't discount Arctic effects, but thinks changes in the stratosphere caused by low solar activity might also be playing a part in slowing the jet stream. The jury is out, he says. I wouldn't rule out either factor, or indeed that they are working together, and the apparent role of stratospheric ozone loss in the acceleration and poleward shift of the southern hemisphere jet shows that stratospheric influences can also be strong on the jet streams beneath. Poles apart. Perhaps the strongest backing for Francis's idea about the northern jet stream comes from the fact that it weakens and wavers most obviously in autumn, right after the September peak of seasonal ice loss in the Arctic Ocean, when the north-south temperature gradient is at its smallest. Many researchers remain cautious about drawing definitive conclusions, however. Modelling studies do show that if all the Arctic sea ice disappears at the end of summer, the probability of blocking episodes increases, making colder spells more likely in the following winter, says Julien Catillot of the French National Centre for Meteorological Research in Toulouse. But recent blocking episodes are single exceptional events, and their rarity prevents us from drawing any conclusions on long-term changes. Well, they'll be bloody happy. They've just had another one that they can look at and measure and model from. Elizabeth Barnes of Colorado State University in Fort Collins is more critical. She argues that the slower and wavier jet stream described by Francis was in fact, quote, an artefact of the methodology, unquote, used to measure the Rossby waves. She has reanalysed Francis's numbers and argues that poleward movement of the northern polar jet stream corrupted the data and that the weather was not sticking any more than it used to. We find no significant increase in blocking highs in any season, she says. Well, ask the Yanks who just had a week at -40. The dispute has got personal, with Francis publicly accusing Barnes of not taking a, quote, balanced approach, unquote, in her work. One leading figure in the field refused to comment on the work when contacted by a New Scientist for fear of being seen to take sides. Ooh! Who says science is not democratic? If the majority thinks that it's bullshit, nobody treats you seriously. Atmospheric physicist Joanna Haigh of Imperial College London strikes a more emollient note. I don't think Barnes is saying this, quote, greater wave activity, unquote, doesn't happen, just that Francis hasn't properly established it, unquote, she says. What this brouhaha does establish is how difficult it is to say with great confidence what the future holds for the jet stream. Most of the big computer models developed to predict climate change, including a new analysis of different models developed for the latest assessment from the Intergovernmental Panel on Climate Change, published online last month, actually predict faster polar jet streams and fewer blocking highs in winter, though more in summer, says Catillot. This would mean more summer heat waves but fewer instances of persistent extreme winter cold. The lengthy review process for the IPCC report meant that it was not able to include an analysis of Francis's recent work. It says simply that, quote, trends in the jet speed are uncertain, unquote. The future of the weather for billions of people depends on who's right, in ways big and small. Sirpa Harkinen of NASA's Goddard Space Flight Center in Greenbelt, Maryland, has argued that jet stream winds also help maintain ocean circulation patterns in the far North Atlantic. Currently, they are directly driven by surface wind patterns which are themselves driven by the jet stream. These include the overturning circulation, sometimes called the global conveyor, which maintains the Gulf Stream that keeps northwestern Europe unusually warm for its latitude. The most important point about the jet stream is how chaotic it is on all timescales, from day-to-day changes to year-on-year and even decadal variability, says Catillot. The growing fear is that, although we cannot exactly predict how things will change, big changes are coming. Such sudden and visceral changes to our day-to-day weather are more likely to bring home the reality of climate change than any gradual changes in average temperature. In some of the most heavily populated parts of the planet, we could be in for a bumpier ride than even climate modellers predict. Yeah, so, Hurricane Sandy last year, now they've just had a weekend in a deep freeze. So, maybe I'm leaping to conclusions and running out of caution, but I would say that in October last year, the matter was up for debate. Now, we have more evidence, and the evidence seems to point towards the fact that the polar jet stream is slowing and oscillating wider and stalling for longer, and yeah, it seems to be targeted at the high population density areas, the industrialised countries, Europe, America, Japan, the places that sort of burn the most carbon. So yeah, you want to have more extreme weather, just keep burning carbon, fellas. It's your choice. You can accept the reality and change your ways, or you can live in denial and your ways will change you into a corpse. Baubles on like YouTube. Put that in your pipe and smoke it. It's not fossil fuel, although the lighter is. Ciao.